Hello, everybody. Thank you for coming to the session on making DNA storage more cost efficient. A sentence probably many of you never expected to hear in your lives, seeing DNA and storage in the same sentence, but here we are. This is going to be an exciting presentation that speaks to a technical collaboration between Catalog, the company for which I'm the Chief Technology Officer, and IBM, with respect to the application of a commercial product that IBM has called the Bayesian Optimization Accelerator that we've applied in our business to find rather substantial savings and efficiencies as a result. So let's begin by introducing the other people who participate in today's presentation, and let me turn it over to Liz.
Hi, my name is Liz Strawman. I'm a data science at Catalog, and I'm really excited to speak with you today.
And I am Matt Drozel, Product and Offering Manager for IBM, and I'm delighted to work with the Catalog team on this amazing new technology they're bringing to market with our help. Dave?
Thanks, Matt. Thanks, Liz. So today's meeting, today's presentation, our conversation will give you a little bit of background in DNA and storage, and then we're going to talk about the problem we have, and we'll show results at the end. So let's begin at the beginning and talk about DNA and why this is important and why this is something significant in the evolution of storage, today's electronic world. So as I said, Liz and I represent Catalog, which is a small company up in Boston, started a few years ago by a couple of MIT scientists. And the motivations really came out of thinking that's been going on for quite some time. So you see, for example, a quote on this page from Bill Gates that characterizes DNA as something substantially more complex and advanced than anything that one could do with storage. But perhaps the more important quote is from Feynman down at the bottom, who talks about really working with DNA at an atomic level, if you were, biological molecules at an atomic level, to see how they could be useful in a domain of computing. And it's really that kind of motivation that we take as a guiding principles for Catalog. So give you some perspective of what motivates us. Let me give you a very quick overview of what's happening in data today. You see two curves on this chart that represent the relative growth of compute against the growth in data. And so you see this progressive gap over time from current period out into the future that gets more and more profoundly exacerbated. These are zettabytes, by the way. These are big numbers, and they're growing at a very dramatic rate. In fact, it's not uncommon today, as you entertain the activities that go on in many, many different market segments, that the amount of data being generated far surpasses what the capability is of the enterprise to actually analyze that data. And so you create this phenomenon that we refer to as dark data, data that probably has value, but no one knows about it because they can't get at it to compute it and so on. So data is growing dramatically. Compute is constrained to an extent as Moore's law starts to grind towards a close. And it opens up the opportunity for new ways to think and do things that were never there before. So let me take you, first of all, to the first kind of mention of DNA as a storage media with Neiman over on the left-hand side of this chart. 1964, only 8 years after the physical representation of DNA was published by Watson and Crick. So he speculates about the potential use of DNA as a storage medium. And then the first discovery of actually implementing that we found was in 1988 with Joe Davis, who happens to be an artist, by the way. And he worked with the molecular biology laboratory at Harvard to encode this picture on the left, happens to be a Germanic rune, into an ASCII-like framework into a DNA molecule. Well, how does he do that? Well, in this case, what they do is, and in fact, what many people still do to this day is they take the bases that form a DNA molecule and they assign values to it. So DNA building block is composed of, DNA molecule is composed of 4 building blocks, A, G, C, and T, and you can assign pairs of values to those particular components, 1, 1, 0, 1, 0, 0, 1, 0, and you can actually, using molecular machinery, begin to actually construct a molecule composed of those building block elements. And the longer the molecule, of course, the more information that you store. In this particular case in 1988, when the molecular tools available were at a very, very embryonic stage, it was just an 18 base pair message that was encoded and put into a bacterium, E. coli, to reflect this Germanic rune. But it was a signal that something was going on here. And DNA, of course, is something that everybody is familiar with, if for no other reason than things like the Jurassic Park movies and so on. But you all have read in lay press and other journals the recovery of DNA from dinosaurs, from insects tens and tens of thousands of years old, embedded into amber, et cetera, mastodons, on and on it goes. So it's a very robust kind of molecule. Okay, so what is Catalog up to? So given that there's been all this tremendous advance in terms of evolutionary achievement with respect to DNA, Catalog has decided to enter the commercial market to leverage the attributes of the DNA molecule to encode data as a storage medium. And if we go from left to right, you get some perspective of what the advantages are that accrue as a result of this. So one thing, of course, is you can encode a tremendous amount of information in a very, very small volume. We're roughly 1 million times denser from a data to volumetric measurement than conventional electronic media. Also, once it's stored in DNA, it never goes obsolete. Imagine saying that about LTO-6 tapes or something like that in the advent of LTO-9 this year. You simply don't have the ability to read back that older kind of media. But as we've noted before, in the case of DNA, 10,000-year-old DNA, yes, we can still read it under the right kinds of circumstances. Now, Catalog differs from other companies that you may have read about beginning to look at the utility of DNA for encoding data. And we've chosen a methodology, which I'll describe in a minute, which we think is at least 1,000 times cheaper than the conventional way that other people entertain. And when I say other people entertain, it's reflective of that Germanic rune encoding, where you look at these bases in the nucleotide and you try to assign values to it. That turns out to be a very, very expensive and time-consuming chemical process that we've tried to avoid. We think that we've found a way to do this cheaper. We've found a way to do it more efficiently. And we think that by virtue of doing this, we'll open up still other kinds of opportunities in the future, including potential use of DNA for computation. Okay, now to the basics. So as sort of a metaphor for how we think about encoding data into DNA, it's important to perhaps think of this as an example using movable type, where you have pieces of things that you move around, and by putting them in the proper order, you convey value to the organization of the pieces that you've moved around. Okay, so in the case of movable type, it might be letters. This happens to be a representation of Korean text, because it turns out that scientists or people in Korea invented this prior to Gutenberg by at least 15 or 20 years. So we give credit for that. But the notion is very simple. You want to reorder objects, and by virtue of the order of the objects, you convey information. So in our case, what we do is we take little snippets of DNA, which are manufactured for us. So these are commercially manufactured. They're synthetic. We design them in all their gory detail. And we get a bunch of this stuff produced by commercial enterprise, millions of these little snippets. We have a very particular set of unique ones, and we take that unique set of little oligonucleotides, or oligos as they're called, and we've developed a process by which we can reorder those in a way very much like movable type. Okay, so a little more detail. So we start on the left-hand side of this chart with this very, very small snippet of DNA. So this is infinitesimally small compared to human DNA, right? This is maybe 20 or 30 base pairs. Again, it's designed by us in terms of what the order of the bases are, and some other attributes I won't go into of a technical nature here as well. It's biologically inert. You cannot take this and turn it into something that becomes biologically active. And there are a lot of different tricks we've done to make that happen so that no one could ever jump to the conclusion that by virtue of manipulating strands of DNA, you could suddenly, for example, give rise to a new life form. That's not what we're doing here. That's actually precluded by virtue of the way we design these molecules. So we create a whole bunch of these, and then they differ from one another as evidenced by the different colors we supply to each of the oligos here. And in the middle, you see a particular combination, yellow, blue, pink, I guess. And that particular order conveys information, and that string of DNA snippets stitched together is what we call an identifier, a data identifier, if you will. Now, important thing to note on this particular chart is how do you sort of stitch these pieces of DNA together? And I'll introduce one technical word for you here. It's called ligation, and it's a chemical process that gets invoked under enzymatic control that will take these different pieces of DNA and put them together in the way depicted in this center piece. I should also mention that the way we've designed the individual pieces precludes them from simply being reassembled in random order. They can only be stitched together in this particular way, okay? And as we do this in volume, you get a lot of different molecules that look like this, different colors and different orders. And in total, they represent an identifier library, if you will. Just a whole batch of small DNA molecules, maybe not longer than 300 base pairs in overall length. Compare that to human DNA, which is 3.5 billion bases. It's a very, very small representation of something that we're all familiar with. Okay, so we start with building blocks. We stitch them together. They're all different from one another. And in effect, we have a combinatorial kind of situation here, which simply means that by reordering the pieces in some interesting ways, we can create uniqueness in terms of the overall molecule that gets created. What this looks like in a data representation is something like this. So we've now created each one of these vertical pieces here represents a different molecule that we've synthesized. They differ in terms of color, and the colors differ in terms of where they're positioned in each of these different molecules. And they all correspond to a bit position in a data stream that's shown on the bottom. So every molecule that we create reflects an address in a bit stream, okay? And then on top, there are numerical values that get translated into this. And if we go to the next chart, what we'll see is practically, since our alphabet of encoding is simply 0 and 1, we only need to print the 1 molecules. And every bit address that has no molecule is assumed to be a 0. So in effect, we print half the molecules that need to be printed. Listen, we could go beyond that. We could put a little attachment on this that gives a very explicit 0 value to molecules and print them, but that's twice the work. Right. So what we're trying to do here is construct a methodology and approach that is efficient in terms of a commercial deployment. So how do we do this? Well, we invented a machine. The machine is called Shannon, in honor of Claude Shannon, father of information theory. And the way you look at this machine is from left to right. So there's a start on the left and there's a stop on the right, and I'll take you through the various stages. It's an interesting machine in the sense that it actually makes use of inkjet printer head technology, which is the print engine up on the top here, in a very, very interesting way. And it works something like this. To assemble all these little snippets of DNA we spoke of in the previous 2 charts, we actually create a droplet of ink that includes a snippet of DNA, the particular snippets that we've already defined, these so-called components. These in turn are dispensed on a movable web, polyurethane in this case, going underneath that print engine that you see on the left. And the nozzles on the print heads deposit little droplets infused with DNA on very well specified locations on this webbing that's going underneath the print heads. That in turn, and by the way, we do hundreds and hundreds of thousands of these per second. And in turn, the webbing carries these droplets of ink infused with DNA into an incubator on the right-hand side, where chemical reactions take place, the so-called ligation that we referred to before, where the individual pieces of DNA in each droplet get stitched together. And then finally, that comes out at the back end of the machine on the right in the pooler, where all the DNA is harvested from the webbing and then either stored or read or some other process is applied to it. I'll give you a picture of that in just a second in an operational sense. So what we see here on the left upper corner is just a photo of the printheads. They're all under electronic control. They in turn are run by computers that we have on our library. We have thousands of nozzles, by the way, operating at any point in time. So this may be maybe the largest kind of print environment of this sort anywhere in the world. And each one of these printheads is working with a different kind of DNA infused in an ink. Below that chart, what you see are the dots that get produced by virtue of those printheads operating. That's actually a camera shot, a high performance camera that we have attached to the machine that takes a picture of the dots. And by the way, we can examine the actual physical structure of the dots using visual analytics to determine if they're working properly or not working properly in the sense of containing the right kind of material and producing the right kind of result. On the right, you see the machine in operation. This is actually a picture of the incubator. So now droplets have been placed on this underlying polyurethane. It's inside an incubator here. Those yellow rectangles are just representations of the DNA that's been encoded. We put a color coding on it to make sure that we can observe that the DNA is being deposited. And this in turn will get stripped off in the last stage of the machine over here on the right in a pooler, and then that's set up for processing for either preservation or for reading. Okay. So where does this take us to? Well, a lot of complexities, as you might imagine here, but the thing I want to convey is we've sort of represented this as if everything works brilliantly well all the time. But in fact, that's not the case. We're dealing in a world of chemistry where there are some uncertainties that are always occurring. So when we talked about stitching these little components of DNA together through this process of ligation, it turns out that that doesn't happen accurately 100% of the time. And it doesn't happen that way because it's a very high dimensional parameter space. You can see examples of that on the left-hand side. We have a lot of factors that come into play that have an impact on that chemical procedure. So there's the nature of the chemicals per se, there's issues of time, temperature, volume, humidity, all these kinds of things. Then the nature of the DNA itself, how concentrated is it, the environment, et cetera, et cetera. So when you look at that and say, well, how do I know how to operate in this space with all these different variables operating simultaneously, it gets overwhelming pretty quickly. And it turns out Catalog spent probably a year or a year and a half running experiments to try to elevate the ligation efficiency of the overall process. And as we can see on the right-hand side, each one of those experiments takes about 1 to 2 days. So it's tremendously costly, tremendously time-consuming to try to ascertain what is the proper combination or the value of all those parameters on the left to produce the best possible result. And of course, we're always changing the parameters on the left as well. We might introduce a new webbing, we might introduce a new dye, and so do you say, well, let's start all over again and waste another year? And rather than do that, we reached out to IBM because of work that we were aware they were doing with respect to the investigation of problems in serial optimization, and engage them in a technical relationship using this commercial product called the Bayesian Optimization Accelerator. And we did that for the purpose of seeing whether or not it could help us with this design of experiments, right? So we have hundreds of experiments, we run them, we get output, we redesign the experiment, we repeat over and over again. Is there a way to do that more efficiently? So to now take you a little deeper into what the Bayesian Optimization Accelerator is about, let me turn this over to Matt Drozdel from IBM.
Oh, thanks a lot, Dave. many people know that I know a great deal about storage, and I'm really excited about new ways of storing things. On the next slide, we see that we have choices that we have to make. And if you're an engineer or you're somebody working in design, you have so many paths that you can go, and we don't have time to take them all. We have to make more intelligent choices. Otherwise, we're going to be simulating forever. And in the past, we've seen that we would just need to have a map and a compass. And with that map and a compass, we could see everything we needed to do. But nobody does that anymore. I look at Liz because she's in Boston and I used to live in the area. We wouldn't think about making a play to get in or out of the city without checking a detailed map and checking all of the traffic that we can see. Liz, it looks like we're not going to be taking the Mass Pike home today, and we'll be going a different way. So that's just an example of making better choices with more information. And we have a history of that. Here I'm showing you some historical people famous for detection, mathematical detection. You know, we've got Sherlock Holmes, we've got the old TV show Columbo, and we've got Reverend Thomas Bayes, and they're all similar to each other, and that they're all looking to get more and more information and changing their theories and changing their ways of moving forward based upon past learnings. In fact, a classic line by Sherlock Holmes' character is, how often have I said that when you eliminate the impossible, whatever remains, however improbable, must be the truth. Now, which one of these is the best? Well, I'm going to say it's elementary. It's Reverend Bayes, because he put a mathematical way of talking about how his thinking went, where I'm taking past learning and putting it into new hypotheses and testing that. And that's Bayes' theorem. Now, in this next slide, you'll see that on the upper right is what Bayes' theorem looks like. It looks kind of complicated, but it really isn't, and we don't have enough time to go into it, but trust me, it's not. What we have done with the leadership of our IBM research team is created a great product called the IBM Bayesian Optimization Accelerator. And it is just like we're doing a catalog, building better products faster by getting to that ideal situation more quickly and at a lower cost. So it is defined for a broad spectrum of applications. It's just not ligation, and I'll give you an example of a few. And it's delivered as a complete appliance. We can plug it into existing simulation environments in order to accelerate what clients are currently doing. Now, where is it applicable? As I said, not just ligation, but it's applicable in many different workloads. For example, we've used it in computational chemistry in order to get to the right places in which to focus. And the same thing with engineering design. Everybody's interested in making more efficient automobiles, making more efficient trucks. How if we focus on the things to move and maneuver to make the solution better, faster, and not every single option. And even drug discovery in these times of COVID, how can we get to a better drug solution more quickly by not testing all of the particular options? Now, when it comes to the workflow of this, it's a workflow that makes the engineer or the researcher or the scientist more efficient. They'll start with some ideas and start moving forward with some ideas and then put them into BOA. And then BOA uses its capabilities to get to work and test some things, test some candidates, and give feedback to the researcher, designer, or engineer for how things are going so that they can evolve their thoughts as well. And I'll show you an example of that. We, inside of IBM, are actually users of this technology. As you're aware, we're in the process of designing our Power 10 processor, and that's public information. And one of the things that we did with BOA was tested it on P10 design for signal integrity. And these signal integrity calculations would take a tremendous amount of time and tremendous amount of work in order to get them done. By applying BOA, we quickly learned what was important and how we could focus on exactly what was important, eliminating all sorts of engineering and computational bias. And you can see the results here. It's sometimes almost too good to believe, but it's true, and it's a documented case study. And the way we deploy BOA is kind of interesting because we're not asking people to take their simulation in a computational environment and throw it away. We want to optimize that simulation environment. So the way we do that is by taking a current simulation HPC environment, add the BOA system to it, and support whatever sort of servers you currently have. And those servers can be anything, even new servers that are coming out. And it plugs into the environment and accelerates the current workloads. And if we have more workloads and we want faster acceleration, we can add BOA nodes because BOA is based upon technology that scales in itself. Now, asking about what it looks like and what does the output look like, I'll leave you with this because I like simple things. And here is an example of an output. We were doing some wine studies using some open source information on that which makes wine to be good. And when we were running these studies, we found out that we may have thought that residual sugar or alcohol content was really important. No, it turns out that it wasn't. We were wrong, and it was the sulfates that were important for wine tasting. So that's just an example of using BOA even outside of a particular traditional HPC design use case. So what I'd like to do now is hand over to Liz to show how she deployed BOA, and she deployed this technology with her work. Liz?
Thank you, Matt. So we applied BOA to improve our design of experiments in optimizing DNA ligation chemistry. We've named this analysis sliding doors because we can see the path through parameter space taken by our chemistry experiments, and we can compare it to the path through parameter space that would have been taken if we had applied BOA to optimize our search. We start BOA by training the model with the same first 10 experiments executed by the chemist. BOA then chooses the next 10 experiments to run in batches. What we see here in these figures is the performance of BOA in blue and the performance of our chemists in green. Our goal is to find the experimental parameter values that produce the maximal ligation efficiency seen as this dashed line marked ideal. BOA is run many times, and the leftmost panel shows the median performance of BOA runs. The middle panel shows the 75th percentile performance, and the right panel shows the best observed performance. We can compare the rate of reaching the ideal performance between BOA and the chemist, and the table on the bottom right quantifies this difference in performance. We can see here that the median expected BOA performance is really large with a 74% savings. The best performance is at 89% savings, and even the bottom 25th percentile still shows a sizable improvement of 62%. Overall, we learned that BOA can provide a substantial speed up to the rate of experimental discovery compared to how chemists performed on their own without the help of BOA. To summarize, we applied BOA in a retrospective analysis for a particular design of experiments problem and found it to be very successful. BOA was able to reduce the expected number of experiments we had to perform by 74% and a best case of 89% savings. This study gave us confidence in BOA to locate the maximally efficient experimental conditions in our DNA ligation system with the benefit of faster time to insight and lower cost. We applied BOA here to one problem, but we see many other venues where BOA can provide us a lot of value. One of our next steps is to use BOA to help us optimize ligation chemistry out of the test tube and on our writer machine. where we use an inkjet printing to deliver DNA components on a webbing substrate moving through the machine. We have seen that as we explore new materials of webbing, the ligation chemistry is behaving differently than our previous experiments. Instead of running hundreds of new experiments to optimize a different system, we are going to feed data, a batch of new data from new experiments into BOA, and BOA will tell us the next set of experiments to run. And we will iteratively find the optimal parameter values for this new system. BOA searches for the global maximum or minimum to an optimization problem, and there was no guarantee that our scientists will have found a global optimal value through a traditional design of experiments approach. BOA can provide a huge impact in reducing time to insight and lowering cost in an AI augmented experimental discovery. Thank you, and I will hand it back to Dave Turek.
Okay, thanks, Liz, and thanks, Matt. So, couple of parting messages I want to convey to everyone. This approach that we've applied, developed by IBM, is not simply for big, elaborate companies. We're a small startup, about 14 people right now. But you can see the benefit of applying a technology like this to let a company like ourselves punch way above our weight. So it has tremendous strategic value, no matter how big or small your company is, because the benefits are going to manifest themselves no matter what. 74% reduction of experimentation on our part is a brilliant result in terms of the opportunity costs that we avoid by having chemists able to do so much more with their time than just run these ligation experiments over and over again. So our expectation is that we'll continue using BOA through the diverse chemistries that we apply in our particular company and the different kinds of problems that we see. And I think while we're doing simply one example here of design of experiments, the general field for design of experiments is quite large. And you're going to find that in consumer products and engineering and many other areas. So please, if you have questions, reach out to myself or to Matt Drozdel. Our contact information here is on the slide. And we want to thank you very much for listening to us today. Have a good day.